General Relativity, Chapter 1, Section 6, the Stokes Theorem. Now, we are doing a little detour here from our General Relativity class so we can get a nice foundation in some basic concepts in theoretical physics. So here we're going to do a line integral where we take the dot product of a vector field with a line element and go around the square. So here we have the value at the point x and y, bx and by here, the two dimensions, and you put in x, y, and z down here to get those vector values. Over on the right side, we move over by delta x, so we have delta x plus x, and we are interested in the field in the y direction, because when we do this integral, this closed line integral, we want the component that lines up either with or against the direction we're moving in. So here we have the value at y plus delta y, and we now are ready to go. We basically take the vector in the first part of our journey and multiply by delta x. The next vector here, multiply by delta y as we move around, and here we have a minus sign since we're moving against the vector. And again, a minus sign there. So that gets you your setup with differentials. And the trick here is to multiply by the other delta and divide by that delta so you don't really change anything. And in this fashion, you have an area. You can see that we're going to promote a line integral to an areal integral. So we do look at here the line integral on the left, and it's going to go to a surface integral. And we notice that what we have up here is simply a cross product component. So noting that cross product component, we can write this out and notice that in this case, the curvilinear case, we have some scale factors in there also. So work this through, and when you do that, and see that this is the third component of the cross product, when you put in the 1, 2, and the 3, and substituting from my variables here, then I want you to see that when you go in the general case for the other components, you will find that you get the cross product in general. This is very, very important, and is a counterpart to the divergence theorem, Stokes' theorem. And take your time to work through all the steps. And basically what this is doing is equating an enclosed vector piercing surface integral, that's for divergence that is, with a volume integral. And in this case, we're doing a line integral, or vector projected along a line loop, and we're doing an equivalent area or surface, enclosed surface integral.